All right, in this video, we are going to move into section 1.8, which is higher order derivatives. This will be the last section of chapter 1. Not really any new rules today. It's kind of a new idea that we're going to need a little bit as we move into future sections. So what we're going to look at today is how do you take multiple derivatives of a function? So essentially, as the title says at the very top, we're going to be finding the derivative of a derivative. So it's very popular, especially in chapter 3, that we're going to need to be able to find a second derivative of a function. So anytime that you're finding the second derivative of a function, it is represented in the following way. We usually will write it using that same prime notation, and we're going to call this f double prime. So you'll put two little apostrophes or primes next to your f. And this is found simply by taking the derivative of your first derivative. So we've already talked about how to find first derivatives, so now you can take the derivative of the function again. Now, while we don't use much past the second derivative, technically you can actually find any derivative of a function that's possible. So for any higher order derivatives, we will usually use the notation f raised to the parentheses of n of x to indicate the nth derivative of f. Usually this will start if you ever make it to the fourth derivative. A third derivative, it's still usually okay to put a prime on there. Once you get to a fourth and higher, we're not going to put all those primes on there. So we will just write it in this notation. For Leibniz notation, since we will do that a couple of times, if you're ever asked to find the second derivative of a function, it will look something like this. You're going to take the second derivative of y with respect to x twice. So if you see this notation that kind of looks like the regular Leibniz notation, these twos tell you to take a second derivative. So what I want to work on today is just practicing taking multiple derivatives of functions. Now, since second derivatives are going to be the most popular for us, that's what we're going to focus on for the first couple of slides. So problems 1 through 4, I want you to find the second derivative of the following function. So number 1 says f of x equals 2x to the fourth minus 5x. So when you're finding these upper derivatives, you'll find f prime of x in the exact same way. So the first derivative of this would be 8x to the third minus 5. And when you go to find the second derivative of your function, just take the derivative of the derivative you just found. So the derivative of 8x cubed is 24x squared, and the negative 5 goes to 0. That is how you find a second derivative. That's all there is to it. Now we can do this for all different kinds of functions, so I tried to mix in a good variety here. So number 2, y equals t cubed plus 2 over t. Now this shows you an example of where you may have to rewrite something to begin with. So since this is second term is the same thing as 2 over t to the first, I'm actually going to bring that t to the top and rewrite this as t cubed plus 2t to the negative 1. That way I can just do my power rule twice in this example. So y prime is going to equal the derivative of t cubed is 3t squared. And then if I take the derivative of the second term, negative 1 times 2 is negative 2. And if I subtract 1 from the power, that's a negative second as well. I'm going to take the derivative of this again to find y double prime. So the derivative of 3t squared is 6t. And then negative 2 times negative 2 is positive 4. And when I subtract 1 from the power, it's t to the negative 3. This would be your second derivative of your function. All right, so continuing the trend, looking up at number 3. F of x equals 3x to the negative 4th power. So let's take the derivative of this twice. So first off, f prime of x would be negative 4 times 3 is negative 12x. And then you get negative 5 when you subtract 1 from the power. And then f double prime of x, negative 5 times negative 12 would give you positive 60. And when you subtract 1 from the power again, you get the negative 6th power. Short and sweet. And then number 4 gives our first example of what happens if you take enough derivatives and everything goes away, which happens sometimes when you do too many derivatives. So for example, number 4, y is equal to 512x. When you start to find the two derivatives of this function, you will find that the first derivative of 512x is 512. And then if you take the derivative of this again, we know that the derivative of every constant is 0. So as you can see, in this example, you actually don't have anything for your second derivative. Now, as we go further, we'll learn what that means and how it applies. But for now, it is okay that you could possibly have zeros as your derivatives. All right, number 5 takes a little bit more work, so I saved it for a slide by itself. But what about one like this? What happens if your first and second derivative don't use the same rule? So number 5 says y equals 2x plus 3 divided by 5x minus 1. So what you hopefully remember from section 1.6 is that when you have a function in the top and the bottom, we call this f and g, because you got one function divided by a second function. And we can say that we can apply the quotient rule here, which is g times f prime minus f times g prime divided by g squared. So when I go to find the first derivative of this function, so y prime, I'll take my g, which is 5x minus 1, multiplied by the derivative of f, which is just 2, minus my f function, which is 2x plus 3, times the derivative of g, which is 5, all of this divided by g squared. I'm not going to take the derivative of this because this looks really ugly. I'm going to try to clean this up as much as I can before I try to find y double prime. So I'm going to distribute this 2 through to make this 10x minus 2. I'm going to distribute this 5 through, and then do note that there is a minus in the front, so I have to change the sign of each of those as well. So 5 times 2 is 10, but that becomes minus 10x. 5 times 3 is 15, but this becomes minus 15 all over 5x minus 1 squared. As you can see in the numerator, we get kind of lucky here a little bit. 10x minus 10x actually cancels. And if you put your two constants together, you should have a negative 17 on top and a 5x minus 1 squared on the bottom. And that is the first derivative of this function. Now, something really nice happens here. There is not an x in the numerator of your first derivative. So when I go to take the derivative of this again, while you can do quotient rule again, and it's not wrong, it may be easier if you rewrite this as a chain rule problem. So I'm going to take this squared term and bring it to the top and rewrite this as negative 17 times 5x minus 1 to the negative second power. When I take the derivative of this using chain rule now, I can say that negative 2 times negative 17 is 34. Leave the 5x minus 1 alone. Subtract 1 from the power to make it negative 3. And then I'm going to multiply by the derivative of the inside, which is 5. I'm going to multiply the 34 and the 5 together, which I believe is 170, but I'll double check that. It is. So this is 170 times 5x minus 1 to the negative third, which is the same thing as 170 divided by 5x minus 1 cubed. These, either form you put it in, is the second derivative of this function. But I wanted to show y'all one where you do the quotient rule first, and you had to do the quotient rule there. Then you have your options for the second derivative. We could have done quotient rule. I chose not to. I decided to rewrite it and do a chain rule instead. While I said we don't usually go higher than a second derivative, I still think it's important for you to see a couple examples of where we do go higher than the second derivative. So in case it does show up, you know what to do. So on number 6, I would like you to find the fifth derivative, excuse me, of y equals x to the 7th minus 8x squared plus 2x. So this is going to seem kind of a lot of writing, but we got to take 5 derivatives here. So I'm going to begin by finding the first derivative, which is dy dx. That would be 7x to the 6 minus 16x plus 2. Then I'm going to move into my weird Leibniz notation. Oops, sorry, didn't put a 5 there. Should be a 2. The number on top and bottom should match. So find the derivative of your derivative. That would be 6 times 7 is 42x to the 5th minus 16, and the 2 goes away. All right, coming up here to the top. The third derivative of this would be, so take the derivative of your second derivative. 5 times 42 is 210 x to the 4th, and the negative 16 goes away. Your fourth derivative of this function would be 4 times 210, which is 840 x cubed. And then finally, the fifth derivative of this function would be 3 times 840, which gives us 2,520 x squared. That is the fifth derivative of your function. Now, while that doesn't really tell us much about anything, it is just a good habit to practice and good thing to work on, that you can take as many derivatives as you like until you get to the number 0. Number 7, similar. I'm only going to do 4 derivatives this time, but I want you to find the fourth derivative of f of x equals x to the negative 2 plus the square root of x. Now, the x to the negative 2 is already written in a form we can work with, but as we've seen numerous times now, you can't leave the square root of x here before you take the derivative. So I'm going to rewrite this as x to the negative 2, and remember, a square root function is written as x to the 1/2. From here, I'm going to find the first 4 derivatives of this function. So beginning with f prime of x. The derivative of x to the negative 2 is negative 2x to the negative 3. The derivative of the second term, I would bring the 1/2 to the front and then subtract 1. That would be negative 1/2. Let's find the second derivative. So let's see, negative 3 times negative 2 is 6, and that's going to become x to the negative 4th. Here you got to be careful with all your fractions. So negative 1/2 times a positive 1/2 would be negative 1/4 x. And if you subtract 1 from the power, that's a negative 3/2. For your third derivative, negative 4 times 6 is negative 24 x to the negative 5th power. And then I'm probably going to do a little scratch work here, because I've got to do negative 3/2 times negative 1/4. So I'm going to do that over here on the right. Let's see, multiplying those together should give you a positive 3/8. So positive 3/8 x. And if you subtract 1 from the power, that is negative 5/2. One more time, and you will notice that as I move into the fourth derivative, I'm going to go back to that notation I talked about earlier. I'm going to put my number in parentheses as my exponent. And here we go. Negative 5 times 24 is going to give you 120 x to the negative 6th power. And then once again, little scratch work here. You got to do negative 5/2 times 3/8. So negative 5/2 times 3/8 would be a negative 15/16. So minus 15/16 x. And if you subtract 1 from the power, that will be the negative 7/2 power. This is the fourth derivative of the original function. It's a little bit uglier, and that can happen sometimes, especially with radicals and a lot of derivatives. Just take your time with your fractions, find them on the side like I did if you need to as you take each derivative. All right, and the last thing I want to go over is evaluating higher order derivatives. So we're just going to do one example of this. I would like you to find the third derivative of your function evaluated at negative 2 if you know that f of x is x to the negative 1 plus x cubed. Well, you can't do the evaluation part of this problem until you find all your final derivative. So the first thing I'm going to do is I'm going to find the third derivative of this function. Now, the good thing is that this is already written in a form that we can find the derivative of. So let's go ahead and do that. So f prime of x is going to be, that would be negative x to the negative 2 plus 3x squared using my power rule. I'm going to find the second derivative. So negative 2 times a negative is positive 2x to the negative 3, and then plus 6x. And then one more derivative, f triple prime of x. So negative 3 times 2 is negative 6x to the negative 4, and then the derivative of 6x is 6. Now, in previous problems, we'd be done. But since I'm going to plug a number into this, I am going to rewrite my third derivative here. I'm going to rewrite it as negative 6 over x to the 4th plus 6. That way, on the next part, when I plug my number in, it's a little bit easier. So this is negative 6 over negative 2 to the 4th plus 6, which is negative 6 over, and in your calculator, you can type in negative 2 to the 4th. You should find that to be 16 plus 6. So this does reduce into negative 3/8 because both those numbers share a 2 in common. And when you find common denominators here, let's see, if I put an 8 on the bottom of the 6 and multiply the top by 8, that should give me 48 over 8. And when I add these two numbers together, your final result is going to be 45 over 8. And that is the third derivative of this function evaluated at negative 2. That ends section 1.8, and that also ends chapter 1 of this class. So one chapter down, 2 chapters to go. In this section, like I said, the big thing was taking higher order derivatives, especially second derivatives. We're going to see a good bit of that as we move into chapter 3. But as you can see, no matter how many derivatives you take, you just keep taking the derivative of the previous derivative. In the next video, we'll move into chapter 2, and we're going to start talking about logarithms and exponential functions. So I'll see you all in that video.